Okay, we're going to look at the opposite of derivative, and what I mean by that is the inverse of derivative. And this thing is going to be called the integral of a function, so we can think of that as undoing a derivative. We're going to see what we mean by that in just a minute, and there are two types that we're going to see. First, indefinite integrals, and secondly, definite integrals. So we want to know what function has derivative 2x. And we know that if we were to differentiate y equals x squared, we would get dy dx equals 2x. The derivative is 2x. And if we think about what else has the derivative of 2x, if we said y equals x squared plus 4, that also has derivative 2x. Or if we said y equals x squared minus 2, the derivative is 2x. So generally, if we said any y equals x squared plus some constant is a function that we want to differentiate, we're always going to get 2x. And so if we go backwards, what function has derivative 2x? We wouldn't say x squared plus 4 or x squared minus 2. We would say x squared plus a constant. So y equals x squared plus c is the antiderivative of y equals 2x. So this is called the antiderivative because it's, again, just the inverse of derivative. So the process of finding this thing is called integration. And what we do is we evaluate an integral. And that solution is going to be the antiderivative of that function that was inside of the integral. Here's our notation. We have this elongated s, that's the integral symbol. And so when we see that, it means that we're going to integrate whatever function is in front of it. So that f of x is the function that we're going to be integrating. And then this on the end should look familiar. That is a differential. That's saying integrate with respect to x. So we'll see dx, or we might see dt to integrate with respect to t. So let's go back to an example that we already looked at. Find the most general antiderivative of y equals 2x. And we said our solution to that, if we take the integral of 2x, and we're integrating with respect to x, the dx is there for, we end up with 2 times, and then we get 1/2 x squared. We're undoing that power rule. And so we end up just with x squared here. But remember, we have to add that constant. So it's the most general form. And off to the right here, we have the integral symbol and the dx. So those things are operators, just like a plus sign or a minus sign. So once we apply that integral and we actually evaluate the integral, it's going to disappear. Same way that the dx disappeared in a derivative. We can always check it. We could differentiate. So this may have looked a little bit different if you looked around the textbook, or maybe you've taken a calc class, or you've just seen them somewhere. We don't have any limits of integration right here. So they would belong right there. We'll see maybe 2 numbers. So what are limits of integration? They are telling us how to evaluate that integral. If we don't have those limits of integration, that's when we have to have that plus c on the end, the most general antiderivative. So no limits of integration, we want to add c. Limits of integration, we're going to see how to solve those in a minute. So if we go back to that same example, we got y equals x squared plus c, and think about what that means graphically. It means that we're going to take the x squared function and we're just going to basically move it up and down the y-axis depending on what constant we're actually adding to it. So we end up with what we call a family of functions for indefinite integrals. As soon as we add that plus c, it becomes infinitely many of the same function, just up and down whatever vertical line it's on. And here are the integration rules in the second column. And you can see that they're directly based off of differentiation rules. So notice that if we want to integrate x to the n, it's going to be x to the n plus 1 over n plus 1, and then we add a constant. And the really important thing to recognize here is that if we wanted to take the derivative of tangent x, we get secant squared x. So that means that we can evaluate the integral of secant squared x dx, and we get tangent x plus c. But nowhere in here do we see the integral of secant x. And that's important because we don't know how to integrate that. All we know how to do is undo differentiation so far. So evaluate the integral of 2x to the 4 minus 4x dx. So we're going to use the power rule, and we can factor out those constants. So we're going to have 2 times x to the 5 over 5 minus 4 times x to the 2 over 2 plus a constant. And there it is simplified. So next, we have the integral of sine of t plus the square root of t dt. So what function has derivative sine t? It would be negative cosine t. And then we want to use the power rule on that square root of t. So that's going to become t to the 3 halves divided by 3 halves, which is the same as multiplying by 2/3, plus a constant. Alright, so a quick note about notation. When we see this capital sigma here, this is always going to mean the sum of whatever's in front of it. And so here we have on top the ending point. The expression for evaluation is in front of it, and the starting point is what's on the bottom there. So this thing is actually going to evaluate to 3 times 1 plus 1 plus 3 times 2 plus 1 plus 3 times 3 plus 1 plus 3 times 4 plus 1. We're ending at 4, whatever that upper limit there is. And if we evaluate this, we end up with 34. And so we're going to need that to move on. So let's say that we have this figure here, and we want to find the area of this thing. So what's the most efficient way of finding that area? So we're going to claim that we could fill it with rectangles and then find the area of each rectangle. We have a width and a height, and we could just add them all up. So let's look at an actual function. We have some function f between a and b, and we're going to shade that in, and we want to know what the area is here. So what we could do is divide up that interval AB into subintervals. And the subintervals are going to be all of equal width. And that width we're going to call delta x, which is given by b minus a over n. So n is actually going to give us the number of rectangles that we are going to end up using here, the number of subintervals that we have. And it's going to look like this. So you can see we can pack them in there pretty well. The width of each rectangle is delta x. And we need the height of the rectangle, which actually isn't too bad because if you notice, it's just going to be the height of the function. And so right there, the height of that first rectangle, if we plug in x, we get f of x. So f of x is actually going to be the height of that rectangle. So for each rectangle in there, the area is going to be f of x times delta x. So in this case, we have 10 rectangles, and if we add them up, we're going to have f of x sub 1 delta x sub 1 for the first rectangle, f of x sub 2 delta x sub 2 for the second, and so on. And we can write that as a summation. Or if we want more rectangles, we could have n rectangles. And that's going to be this summation from I equals 1 to n. But this is still just an approximate area. We should change that to an approximation. If we want to fill in this area completely, we need infinitely many rectangles. And so we can do that by sending n to infinity. So if we take the limit as n approaches infinity of that summation, that's going to give us the exact area under the curve. Alright, so definition. The definite integral from a to b is given by that limit, provided that it exists, and it's defined by the integral from a to b of f of x dx. And so the fundamental theorem of calculus is going to tell us how to evaluate that. And before we actually state it, this is the most important theorem in mathematics. Most people would agree. Without it, most of our technology wouldn't exist. Moon landing wouldn't have been possible. Physics wouldn't be possible. And so it basically holds up a lot of the sciences. So the fundamental theorem of calculus says that if we want to evaluate the integral from a to b of f of x dx, it's going to be f of b minus f of a. So that's a capital F of a and a capital F of b that are written there, where big F is the antiderivative of f. So we evaluate the integral, we plug in b to the antiderivative, and subtract a inside of the antiderivative. And that's going to give us the area under f on AB above the x-axis. Alright, so evaluate the definite integral from 0 to 3 of 2x dx. So what we're actually doing here is calculating the area under the function y equals 2x on the interval 0 to 3. So we know that 2x is going to become x squared. If we evaluate that from 0 to 3, it's going to be x squared from 0 to 3. And so that means we have 3 squared minus 0 squared. So that area is going to be 9. Next, we have the integral from 1 to 4 of x squared minus 4x plus 6, and that's going to be a parabola. And we're finding the area under that parabola from 1 to 4. So first, if we integrate this, x squared is going to become 1/3 x cubed. We can factor out that 4, and then we have x squared over 2. And 6 becomes 6x. And again, we're evaluating from 1 to 4, so that means we plug in 4 first, and then we subtract 1 plugged into it. So it's a little bit of arithmetic there, but we end up with 9 again, and that's just a coincidence.